Hi everyone. I'm honored to present our latest work accepted at ICCV 2025, titled EC Flow, Enabling Versatile Robotic Manipulation from Action-Unlabeled Videos via Embodiment-Centric Flow. This project explores how we can train robotic manipulation policies from videos that contain no action labels, which is a major challenge in scaling robot learning. This work is a collaboration between the Institute of Automation at the Chinese Academy of Sciences and UCAS, and I'd like to acknowledge all my co-authors for their contributions. Let's dive in. In this work, we focus on a key problem in robot learning. How can we train robotic manipulation policies from videos without any action labels? Most existing methods follow the Vision Language Action, or VLA, paradigm, mapping visual inputs and language instructions directly to robot actions through imitation learning. However, these methods rely heavily on datasets with low-level action annotations, which are expensive to collect and often noisy, reducing robustness. For example, the OpenX embodiment dataset aggregates data from over 60 datasets and 500-plus skills, but still requires consistent action labeling across a wide variety of embodiments, a process that doesn't scale easily. In addition to learning from action-labeled data, recent approaches have started to explore learning from unlabeled videos by predicting object-centric flow. The idea is to infer robot actions by observing how objects move between frames. Here's how it works. At time t, we sample some 2D points on the object. Using the depth map, these points are projected into 3D space. Then, we apply a transformation matrix t along with the camera parameters to estimate their new 2D positions at time t+1. At the same time, a learned object flow model predicts the 2D displacements directly. The difference between these two is called the reprojection error. By minimizing this error, we can estimate the optimal transformation matrix t, which indirectly reflects the underlying robot motion. However, this approach has several limitations. First, it assumes objects are rigid, which breaks down for deformable materials. Second, it struggles with occlusion because the method relies on observing visible object motion. And third, it fails in non-object displacement scenarios like pressing a button or rotating a switch, where the object doesn't visibly change position. These challenges limit the generalization of object-centric flow in more diverse real-world settings. Our key insight is to shift from predicting object-centric flow to predicting embodiment-centric flow. This avoids many limitations, such as relying on object properties, and allows generalization across both rigid and deformable objects. It also makes the model more to occlusion and tasks without clear object displacement, like rotations or fine motions. We introduce EC Flow, a framework that predicts robust embodiment-centric flow directly from action-unlabeled videos. To build our dataset, we start by segmenting the robot using a combination of grounding Dino and SAM2, guided by the text prompt, the robotic arm. Then, we randomly sample key points within the mask and track them across time using the co-tracker model. This gives us a clean representation of embodiment motion without needing action labels. Our model is built on a DT-based architecture, which predicts the motion of these tracked points in a diffusion process. To ensure proper object interaction and alignment with language, we also add a goal image prediction task as an auxiliary branch. This helps the model focus on the outcome of the manipulation and grounds the motion prediction more semantically. To calculate actions from the predicted flow, we need to consider the articulated structure of the robot. Unlike previous methods that only consider the end effector as a single rigid object, EC Flow models each joint's motion separately. This is critical for handling real-world robot kinematics. Our pipeline has two steps. First, we allocate the sampled key points to different joints. We do this by using the URDF file to project each joint's 3D geometry into 2D and assign each point to the joint whose bounding box it falls into. Second, we estimate the end effector's transformation. We start by lifting the 2D point flow into 3D using depth. Then, we compute the joint transformations relative to candidate end effector poses using URDF-based inverse kinematics. Finally, we find the optimal end effector pose by minimizing the reprojection error between the predicted 2D motion and the motion induced by the estimated transformation. This gives us a physically plausible end effector action that can be sent to the robot controller. We evaluate EC flow in both simulation and real-world environments. In simulation, we use the MetaWorld benchmark, which includes tasks involving occlusion. EC flow outperforms all baselines with a significantly higher average success rate. It achieves near-perfect performance on tasks like button-top press and hammer strike, where occlusion makes motion prediction difficult. In the real world, we test on tasks involving non-rigid objects or subtle actions with minimal displacement. EC flow again outperforms previous methods, especially on tasks like folding towels, pressing a mouse, and rotating a switch. Overall, EC flow shows strong generalization in 3 challenging settings: deformable object manipulation, occluded scenes, and tasks with non-object displacement motions. Here, we visualize the results of our EC flow method. On the left side of each column, you can see the predicted embodiment-centric flow based on the goal image and initial observation. On the right, we show the actual execution of the action derived from that predicted flow. These examples include tasks like folding towels and opening drawers and ovens, many of which involve occlusion, deformable objects, or minimal object displacement. The results show that EC flow can generate accurate and physically executable actions directly from video, even in challenging real-world settings. We also explore the use of cross-embodiment data by combining human and robot videos. In this experiment, we focus on 2 tasks: door opening and door closing. We use only 2 robot demonstrations per task, and gradually add human videos from the something v2 dataset. Human videos alone cannot transfer directly, but even a few robot examples combined with human motion priors lead to noticeable gains. With 50 human videos and just 2 robot demonstrations, we achieve a 70% success rate, a significant improvement over using robot data alone. This suggests that accessible human videos from the internet can greatly improve data efficiency and help robots learn general action patterns. Finally, we note a few limitations. First, predicting embodiment flow and decoding actions can introduce small errors that accumulate, reducing precision. Second, when the action space is large, for example, when consecutive actions are far apart, decoding becomes slower and more difficult. Addressing these challenges is part of our future work. To summarize, EC flow offers a new perspective on learning robotic manipulation from unlabeled videos by shifting from object-centric to embodiment-centric flow. It enables robust action prediction across occluded, deformable, and subtle manipulation scenarios, even with limited robot data. We also show that incorporating human video can further enhance generalization and data efficiency. Thank you for your attention. You can find more details on our project page, and feel free to reach out via the contact QR code if you have any questions or would like to discuss further.